Chemistry, we're going on to our fourth lesson in Unit 6, and this is on creating covalent structures. We're going to learn how to draw a molecule, a covalently bonded molecule, using Lewis dot structures. So there are two goals when creating a covalent bond using Lewis dot structures. One, all valence electrons contributed by the bonded atoms must be placed in the molecule, and all atoms have full octets, with limited exceptions to be discussed later. So I'm going to go through the rules. They won't make a lot of sense entirely until you actually get into some examples, so let's just get through these. One, determine the total number of valence electrons. You just count up the valence electrons in all the atoms being bonded. Two, you make the best effort you can to draw the structure. It's a little bit of guessing, but don't worry about that too much. It's usually just drawn the way you might think it would be drawn. So A, the least electronegative atom occupies the center of the molecule and is usually written first in the formula. B, hydrogen and fluorine must occupy outside, called terminal positions. 3, connect the outside atoms with the central atom using single bonds. 4, create octets for all terminal outside atoms. 5, assign remaining electrons as lone pairs around the central atom. And 6, form multiple bonds with the central atom if necessary. So we'll go through these one by one as we create three structures here in this lesson. So we're going to start with water, H2O. So rule 1, determine the total number of valence electrons. So hydrogen, there are two atoms, and each hydrogen has one valence electron, the electron in its first orbital. That's a total of 2 electrons. Oxygen, there's one atom, and it has 6 valence electrons. So if you don't remember how to determine that, you start over on the left side of row 2 with lithium, and you count how many elements you have to count over to get to oxygen, and it's 6 elements. That means it has 6 valence electrons. So there's a total of 8 valence electrons in the water molecule. So a water molecule has a total of 8 valence electrons. So now we're going to draw the structure. The least electronegative atom occupies the center of the molecule and is usually written first. So the least electronegative is hydrogen. Hydrogen is less electronegative than oxygen. Rule B, hydrogen and fluorine must occupy outside terminal positions. So there's a conflict there. Hydrogen's the least electronegative, but Rule B says it has to occupy the outside positions. And so the way we're going to draw it is with hydrogen on the outside. Hydrogen simply cannot be a central atom. A central atom has to be able to bond in 2 or more locations, and hydrogen can only bond in one location. That's why it must be an outside atom. So we're going to put oxygen in the center and the hydrogens on the outside. Now we don't know the shape of this molecule, where those H's should be. We're going to learn that in a later lesson, how to use these structures to determine the 3-dimensional geometric shape of a water molecule or any other molecule. So we're just going to assume it's symmetrical, with an oxygen in the center and 2 hydrogens, a hydrogen on each side. So rules 2A and 2B conflict. Hydrogen is less electronegative than oxygen. However, hydrogen can bond in only one location, so hydrogen cannot be a central atom. Therefore, oxygen is placed as the central atom. Okay, so 3, connect the outside atoms with the central atom using single bonds. So there we've done that. So now by doing that, we've used 4 of the 8 valence electrons. When we're finished with this structure, there must be 8 electrons, 8 dots on the paper representing those 8 valence electrons. We've used 4 of them here. 4, create octets for all terminal atoms. Well, hydrogen already has a full octet because hydrogen can only hold 2 electrons in its valence orbital, its first orbital. So that's been taken care of, so it has full octets. 5. Assign remaining electrons as lone pairs around the central atom. So there we go, we just did that. Rule 6. Form multiple bonds with the central atom if necessary, but this rule is not necessary in this example. So this is a complete Lewis dot structure for a water molecule. Okay, so everybody has a full octet. The hydrogens each have 2 electrons, which is a full octet for them. The oxygen has a full octet, 8 electrons. And we've used all 8 of the electrons that we determined at the beginning of this example we had to have for valence electrons. So the 2 requirements of a covalent bond have been met. 1, all valence electrons have been placed, all 8 of them. And 2, all atoms have full octets. 2 other notes about the Lewis structure for H2O. 1, the bonding electron pairs can be represented by a line. We've seen that before, and you can see that down on the example on the right. The non-bonding lone pair electrons cannot be shown in this way. You cannot use a straight line for non-bonding electrons. In fact, oftentimes when you use the straight line notation that you see on the right, you do not show the lone pair electrons. It would simply be an H, line O, line H, and you wouldn't show those 2 lone pairs. You can do it either way. 2, water is not a straight linear molecule as shown below. The rules for determining the geometry of molecules will be covered later. Okay, now we're going to do oxygen, O2. Determine the total number of valence electrons. So there are 2 atoms of oxygen. Each one has 6 valence electrons, 6 electrons in its second orbital. So that's a total of 12 valence electrons. So when we're done with this structure, we must have 12 dots on the paper. An oxygen molecule has a total of 12 valence electrons. So we're going to draw the structure. The least electronegative atom occupies the center of the molecule and is usually written first. Hydrogen and fluorine must occupy outside, called terminal positions. Well, O2 is a pretty simple molecule. There's just 2 oxygen atoms, so you just put them side by side. There's not a lot to deal with there. Both oxygen atoms are considered central atoms. 3, connect the outside atoms with the central atom using single bonds. So there we go. We put a single bond between the 2 oxygen. So now we've used 2 of the 12 valence electrons we have to place. Four, create octets for all terminal outside atoms. So both of the oxygens are also terminal atoms, or both central atoms and terminal atoms. And there we did it. So both oxygens now have complete octets. But when we count how many electrons we have there, if you count all the electrons there, there's 14. We only have 12 to work with. So reduce the number of electrons to the number computed in step 1 by eliminating lone pair electrons. Assign remaining electrons as lone pairs around the central atom. Okay, so we have 14. We have to limit it to 12. So we're just going to take off one of those lone pair. That would be 2 electrons. So we just arbitrarily chose those 2. So we can choose which lone pair to remove. So there it goes. So now we're down to 12 electrons, and that's what we need. Now what we need to do is, without adding or subtracting any electrons, we need to rearrange those so that both molecules have an octet. So think about that. How can you do that? You have 12 electrons there. The oxygen on the left has an octet. The one on the right only has 6 electrons. What can you do to give both of those an octet? So form multiple bonds with the central atom if necessary. So here we go. It's necessary in this case in order to give both an octet. So watch this. We're going to take that lone pair and put it in between. So we have met both requirements for a covalent bond. We used all 12 of the valence electrons and recreated octets around both oxygen atoms. So this is how you know that oxygen has a double bond, is because the only way you could arrange the 12 electrons that you had to work with so that both of them had 8 electrons. The one on the left has 8 and the one on the right has 8, because those 4 central bonding electrons are counted for both of the atoms. The only way you can do that is to give oxygen a double bond. Now we're going to do HCN. So determine the total number of valence electrons. So hydrogen, there's one atom, it has 1 electron. Carbon is 1 atom, it has 4 electrons. And nitrogen is 1 atom, it has 5 electrons. When you total those up, you get 10 electrons. So that means we have to have 10 dots on our paper when we're done with this bond. An HCN molecule has a total of 10 valence electrons, which must be placed in the molecule. So draw the structure. Well, this is pretty straightforward. You're not sure which one goes in the middle, so let's follow the rules here. The least electronegative atom occupies the center of the molecule and is usually written first in the formula. Hydrogen and fluorine must occupy outside positions. So carbon is less electronegative than nitrogen, so it's the leading candidate to go in the middle central atom. So electronegativities from the periodic table of electronegativities: hydrogen is 2.1, carbon is 2.5, and nitrogen is 3.0. So H has the lowest electronegativity, but it cannot be a central atom. This makes carbon the central atom. And so the structure is going to be just the way it's written in the formula, HCN. So connect the outside atoms with the central atom using single bonds. Okay, so there we have 4 electrons. We've used 4 of the 10 electrons that we have to be able to place. We have now used 4 of them. Rule 4, create octets for all terminal outside atoms. Hydrogen already has an octet because it has 2 electrons. That's all hydrogen can hold. Nitrogen, however, we can go ahead and place the additional electrons around nitrogen. So nitrogen now has a full octet. So how many electrons have we used? We've used 10 electrons, and that's how many we have to work with. So we've met one of the 2 rules we have to meet. We've used the proper number of electrons, 10. However, the problem is carbon does not have an octet, so we need to figure out a way to rearrange those electrons without adding or subtracting any of them, rearrange them so that everyone has an octet. Nitrogen has 8, carbon has 8, and hydrogen has 2. So we have now used the 10 valence electrons, however, carbon does not have an octet. Rearrange the lone pair electrons to create an octet for carbon. And that's how you do it. Create octets for all terminal outside atoms. Rearrange lone pair electrons to create an octet for carbon. So the only way to do that, the only way to get that to happen, is to create a triple bond between carbon and nitrogen. By the way, we'll learn more about bonding later. There's nothing bigger than a triple bond. There's no quadruple bonds. You can either have single, double, or triple bonds in a molecule. We create a triple bond with carbon and nitrogen. This fulfills the 2 requirements for a covalent bond. 1, we used all 10 valence electrons, and 2, we have created octets for all elements. The 6 electrons in the triple bond are counted for both carbon and nitrogen. So elements in group 13, starting with boron, are exceptions to the octet rule. Elements in group 13 compounds have only 6 valence electrons. So look at the column that has boron B in it, and the elements that are in that group, that means going down. So boron has 6 valence electrons in the compound boron hydride. So that would be considered a complete molecule. All the hydrogens have full octets, 2 electrons. The boron has 6 electrons in its octet, not 8. Again, it's an exception to the octet rule, but that's considered a complete molecule. Aluminum has 6 valence electrons in the compound aluminum chloride. Aluminum is right below boron on the periodic table, so it's in the same group. Okay, one last concept to cover. How do we tell the difference between ionic bonds, polar covalent bonds, and covalent bonds? So remember, covalent bonds, the electrons are shared equally. Polar covalent, they're pulled a little bit more towards one of the atoms than the other. The one with the higher electronegativity pulls the electrons a little closer. And ionic bonds, one of the atoms totally takes the electrons away from the other atom to give it a negative charge, and then the other atom has a positive charge. So how do you tell the difference when it is actually going to be ionic, polar covalent, or covalent? So there's actually a numeric way to tell that. So the following table gives a set of guidelines for classifying the 3 types of bonds. The classification of a bond can be determined by the electronegativity difference between the 2 elements, as shown below. So an ionic bond exists if the electronegativity difference between the 2 elements is greater than 2.0. So let's take an example. If you look at your periodic table of electronegativities, fluorine has an electronegativity of 4.0. Calcium has an electronegativity of 1.0. The difference between those 2 numbers is 3. That's greater than 2.0. Therefore, when fluorine and calcium get together, the fluorine is strong enough to totally take the electrons away from the calcium, and that's going to create an ionic bond. Okay, next, how about water, H2O? Oxygen has an electronegativity of 3.5. Hydrogen has an electronegativity of 2.1. The difference between those two is 1.4. So 1.4 lies between 0.5 and 2.0 there on the table. That would make water a polar covalent bond. The oxygen doesn't totally take the electrons away from the hydrogen, but it does pull them more over to the oxygen side of the molecule. And finally, if you took any diatomic molecule like O2, there's no electronegativity difference. Both atoms have a 3.5 electronegativity, so there's no difference between them. They're both equally strong, and therefore that's going to be less than 0.5, and so that would just simply be a covalent bond. Example, what type of bond does HCl form? H has an electronegativity of 2.0, and Cl has an electronegativity of 3.1. H has an electronegativity of 2.1, and C has an electronegativity of 3.1. The electronegativity difference is 1.0. This means that HCl is a polar covalent bond. All right, and that takes care of this lesson on creating covalent bonds, and you're going to see how these structures can be used to do some pretty sophisticated analysis on a molecule, including what is its shape, what geometric shape does it have in 3 dimensions, and we'll do that in a later unit.